programming. I'm not too good at it, so there's not that many common patterns I've seen across problems. Because DP can mean anything, to be honest. But for some of the simpler ones, here are some of the patterns that I observed in terms of template. So, um, for example, this jump problem tells you to count the last index and the minimum number of jumps. So any of these problems where you're trying to minimize or maximize something or count or combinatorics and things of that nature, one of the things that you should think about is DP or dynamic programming, using some previous information to inform the next piece of information. So here we're trying to minimize something, that is the number of jumps to some end goal. And I won't go through the details of the problems here because I don't think that's germane. But just know that a lot of times you need some auxiliary matrix to go in parallel with the supplied matrix or array to basically use it as a table to kind of jot down how many steps or what's the minimum of steps to reach, step I or index I or what some position, right? So here you see that I instantiate this, but this is optional because sometimes you can directly edit the array in and of itself to arrive to the answer. In this case, it's more convenient to use this new data structure to tabulate things as opposed to the existing one. And a lot of times, but not all the time, which is why DP is hard, you would have initialization value that's very different because we're trying to minimize stuff. By default, all these other values have to be very, very large. And then, for the 0th index, you have to think about, should I initialize it at 1 or 0, and that's problem specific. Another thing is oftentimes you'll see that here it's the total length is length of this array, but sometimes you might want to add an extra element in front of, so like it will be length of nums plus 1 will be an entire array, just because there might be some implicit thing, like an empty string, like if you're doing like a string path or string interleaving, which I'll talk about below, or something like that, you might actually want to have like for example here, an extra element. So do you have like a null case or empty case that it would be valid and would be a convenient thing to use in your DP algorithm? If yes, then you might actually have this length be 1 more. But one thing in all DP cases, you have to loop through your DP array, and you do some condition checks, and then you update your array. So this is, these boundary checks are not problem specific, because obviously if you don't do boundary checks, then you're going to step out of the array and get a key error. It won't, it just would be a runtime issue, right? So, and then you update your array, and then this is, I would say this part there's no real pattern, but it generally depends on some subset of its neighbors to update this value. And I would say coming up with this formula is the hardest part of any DP problem, because you have to find a pattern and then you have to do that. Unfortunately, there's no like fast and simple way that I know of currently to come up with this answer, right? It's kind of like just drawing out a table and then kind of noticing patterns and then being like, oh, like then in that case this must be true, because I've seen it so many times in the table I've sketched out, and then also like I can kind of semi-formally prove it in my head that this must be the case. So let's look at another DP one. This is another array initialization here. Once again, this is just trying to see if string 1 and string 2 interleave to form string 3. Interleaving is just basically like if you interleave your fingers, like as a prayer, you can kind of like shove 2 fingers into between your index and middle finger, or 1 or whatever. But basically, like, can these two basically come in order to form S3? This is a more formal definition. Problem again isn't too interesting. You want pause the video, just read this. So here, there's just 3 strings, right? So there's no tabulation structure here. It turns out that string 2 and string 1 are basically going to generate a 2D DP structure, and this 2D DP structure basically says I want to go right or down to traverse to S3. And basically, if I'm like here at position 2, 0, that means like the first 2 characters of S1 going to S3, and then like if I'm over here, that means the first 2 characters plus the first character of S2 is the first 3 characters of S3, and vice versa. So that's what this mapping is, and I think coming up with this mapping, again, is problem specific, and that's probably the hardest part. So if you come up with the hardest part, you might as well just not get hit, like, if you spend like 15 minutes coming up with the hardest part, you might as well memorize this, so then the last 5 minutes is like a breeze to actually convert it into code. All right. So yeah, here we initialize some conditions, and then like I said previously, these boundary conditions, or this like first thing, is gonna be some special value, so then your DP array can kind of propagate this information across the entire array, because without this, then there's nothing to propagate. So yeah, here in this case, it's the 0, 0, that's special case again. Here we loop through the DP array as you would here. And then here, one of the things not to get tripped upon is, again, the boundary checks for runtime issues. And what I like to do, so there's no real boundary conditions here because it's a 1D array, and I'm doing for I from 0 to length nums. But here, the DP, and this DP looks into neighbors that can be out of the bounds of the DP table. So really, what I like to do is have this case that's just a common case where you're inside and you're not in the boundaries, and then there's this case where you have I equals 0, but then keep in mind you should have j is more than 0 and not greater to equal to 0, because if you're looking to the left, then 0 can run you out of bounds. Symmetrically here, j equals 0, I is greater than 0. So like these 3 conditions are basically like, if you're going to fill in the DP table, like you can't go wrong using these if, else if conditions and never run out of bounds, and then you can kind of just double check that your things are good. Now obviously if you have some weird DP problem where you do like j minus 2, then obviously then these needs to be updated to j is greater than 1, and j is greater than 1 here, because if j minus 2, then the minimum you need is 2, right? And if it's easier for you to pattern match, then you could do greater or equal to 1 to satisfy this 1 here, and 2 to satisfy 2. So you don't have to like have cognitive burden of like doing this minus 1 greater than thing. You just include it. Up to you. Yeah, I mean, that's all I have to say for DP, because most of the DP's difficulty is actually coming up with the problem. But these boundary checks will actually be somewhat helpful, because it'll save you a bunch of debugging. It sounds obvious, but when you're kind of in the middle of like a gun pointing at your face, it's a little bit, let's say, a little bit more convenient to just have these things memorized and known, and just to watch out for. So then, at least if you're debugging, then you know exactly like, oh man, like there's a out of index error. Let me just take a look at these things first, and it'll definitely cut down on your debug time. I would say a lot of times for DP, these are the most like the boundary is the most common mistake I make, and then the second most common mistake is like the actual algorithm, which is the hard part. But anyway, yeah, that's it. Hope that helps.